Can you hear me? Okay. Thank you for introduction. Hello, everybody. Isaku Yamahata. In this presentation, I'd like to introduce Ryu SDN framework, and I'd like to share my Python experience. In fact, I'm a bit surprised that I have so many audience. In fact, 2 years ago, I gave a presentation on Ryu. I had only 2 audiences. So this is a very glad surprise. Okay, this is the agenda. At first, I'd like to discuss about SDN as an introduction, a background of Ryu project. And then next, I'd like to introduce Ryu project, Ryu itself. And then I'd like to discuss about its internal implementation internals. And especially, I'd like to show the details of OpenStack integration. And then I'd like to have a look at brief look at its development process. And as a last discussion, I'd like to share my Python experience. At first, my self-introduction. Who am I? My background is OS and virtualization development. Not a network guy or Python expert. My primary programming language is C and assembler. So far, I have contributed Linux-related open source projects like Linux kernel. In fact, I have a publication on Linux kernel internals, and I have contributed Zen hypervisor, KVM hypervisor, and QM hypervisor. And recently, I'm working on OpenStack cloud software and OpenV switch. Software OpenFlow switch, and for last 2 years I've worked on Ryu project. So my Python experience is 2 or 3 years. So I'm not a Python expert. Okay, I'd like to discuss about Ryu project background. So recently, SDN. Software-defined networking is a buzzword. So many media talks about SDN, and many ventures or big or small companies are working on SDN-related products. In one word, SDN is to make network programmable. That's it. It's very simple. Idea is very simple. And this kind of idea is not new idea. So far, many people proposed similar ideas, but SDN is the first one that gained big movement. There are several reasons. One of the reasons is industry technology trends. Recently, virtualization and cloud technology makes OS management very flexible. But network side is behind those technology progress. So some innovations in network technology area is necessary. So virtualization or cloud technology makes OS management very flexible and automated. So networks needs similar network is required to be flexible as much as possible. So what is the SDN architecture? What's the difference from conventional networking? This slide shows the difference. Left side shows conventional networking. Each network device is built in a single hardware, built in a single box, and hardware and its software operating system and its features are built in a single box. And this box is provided by switch vendors. And it is very difficult for users to modify this, modify or change this box. And this evolution is controlled by switch vendors. So its progress is slow compared to OS or virtualization or cloud software. So basic idea is to make these features, to move these software out of the box and make those softwares a common program. Right side shows SDN, how SDN organizes network. This red circle shows hardware and its operating system and features move out from hardware to the outside. And this slide shows its details of SDN architecture. The hardware has only a simple feature to forward packets, only forward packets, and its intelligence is out of the box. And one of layer on the above hardware controller layer. There is a controller layer, and it provides it communicates with hardware via a well-defined interface, controller to data plane interface, like OpenFlow. And the controller layer provides a more abstracted API to business logic, and application layer implements its business applications, and application layer realizes useful network behavior. So as a controller to data plane interface, OpenFlow is the most popular protocol. So I'd like to introduce OpenFlow. OpenFlow is just a protocol to control switches. OpenFlow switches, Ethernet switches that support OpenFlow is called OpenFlow switch. And it has an OpenFlow protocol layer, and it can communicate with OpenFlow controller outside of the box. And the OpenFlow controller talks to OpenFlow switch and controls its forwarding, controls how OpenFlow switch forwards packets. And this picture shows how OpenFlow models packet forwarding. Packet forwarding. When a packet OpenFlow switch has a flow table, and it has a matching table against packet header. When packet comes into a port, OpenFlow switch matches against flow table and try to find a matching entry. If matching entry is found, there is an action here. And OpenFlow switch executes its action. And based on this action, OpenFlow switch forwards the packet to other ports or drops the packet. And if matching entry is not found, the packet is sent to the OpenFlow controller. And then OpenFlow controller passes packet and try to figure out how to handle this packet. and populates necessary OpenFlow entries. And then let OpenFlow switch go on. And then packet is processed. And the packet is processed. And packet forwarding is done. This is the basic model of OpenFlow. This is very this model seems very simple, but this is very powerful. Okay, I'd like to move on to Ryu itself. Ryu is a software-defined networking framework, and it's a component-based. Ryu is named after Japanese. There are two kanji characters in Japanese whose pronunciation is Ryu. One is Ryu, and it means flow, like this. And another character is Ryu. It means Oriental dragon, a god of water. It can manipulate water freely. So Ryu SDN framework controls packet flow to enable intelligent networking. So its feature, Ryu is component-based. And it is released under Apache v2, so anyone can use it freely. And it is written in full Python. It doesn't have any C Python module. So it is very easy to understand and easy to modify. And Ryu is not only a OpenFlow controller, but also it is able to handle many other managing network protocols like netconf or SNMP. So it supports OpenFlow protocol because Ryu started as OpenFlow controller. And it also supports non-OpenFlow protocol like netconf, OSDB, NetFlow, SFlow, VRRP, SNP, and so on. And the Ryu project allocates its own SNMP enterprise object ID. And OSDB is open protocol that which is used to configure Open vSwitch. So Ryu is able to configure Open vSwitch without any other component. And Ryu comes with many useful features and libraries. It has a packet library. It can pass a packet and Ethernet packet and packet. This can be used by any other project. And Ryu supports STP and LHCP and so on. And Ryu comes with many useful sample apps. And some of sample apps is really useful for production use. And also, Ryu is able to convert OpenFlow packets to JSON representation, and it is able to communicate from outside with RPC. And Ryu is integrated with other famous projects like OpenStack or HA, Zookeeper for HA, or with Snot for IDS. Okay, I'd like to introduce some useful features which comes with Ryu. One of useful features is REST API. Some REST APIs are provided, OpenFlow control or firewall or router. they can be controlled with REST APIs. So you can use your favorite program to talk to Ryu. OpenFlow control REST API is used to insert or delete OpenFlow entries. And firewall API is used for configure firewall. Based on L2 L3 mapping, the packet can be dropped or passed based on the rule that you installed. And the router REST API is used to control a router. You can install routing table into the switch via REST API. This is very useful. Another useful feature is Topology Viewer. This is when Ryu comes with a topology discovery component, and it tries to discover network topology by using LLDP packet, and you can see the result by web browser. It looks like this, and this is very fancy. Another good feature is HC support. OpenFlow controller can be a single point of failure, SPOF. So if OpenFlow controller fails, the entire network fails. That is very bad. So HC is highly required. You can work with Zookeeper to detect Ryu controller failure, and and when Ryu master is failed, it is failed or takes over by slave Ryu controller. Okay, another good feature is IDS support. You can install a Snot component, IDS component can program the program OpenFlow switch to duplicate packet to IDS, in this case Snot. When packet comes from the port, the packet is duplicated to Snot, and it is passed to the useful, in addition to real destination. And when Snot detected intrusion, the alert is sent to the Snot component, and then Ryu can take actions on it. For example, logging the intrusion. Okay. So far, I had introduced Ryu features. Then next, I'd like to talk about Ryu internals. Okay, Ryu program. Basically, Ryu is a quite normal program, I think. It doesn't use any special tricks. And its program model is event-driven. Because OpenFlow model is event-driven, so this is a very natural decision. In fact, many OpenFlow controllers is based on event-driven. So Ryu's core is its event dispatcher, and its size is very small. And the event dispatcher can be used for general purpose. It is not restricted to OpenFlow. And Ryu's feature is Ryu's characteristic is component-based. Almost all almost all features are modularized as a component. Even OpenFlow related code related codes are component. And those components communicate via events, not directly. This picture shows Ryu architecture. You can see this follows standard SDN architecture. And at hardware level, there is hard network devices. Some network devices can be OpenFlow switch. Some can be conventional IP network devices. And Ryu communicates with OpenFlow protocol over some existing network protocol, netconfig or netconf or something. And Ryu implements in the Ryu, there is a protocol layer. It passes or serializes protocol, OpenFlow protocol or another protocols. And at the core, there's an event dispatcher and libraries for Ryu apps. Ryu apps is Ryu abstraction of application layer. Ryu comes with some useful built-in apps like tenant isolation or topology discovery or firewall, which I introduced in previous slides. And also you can program your own Ryu apps. And if you don't like Python, you can be controlled via over a REST API or RPC. So you can build your own SDN applications in your favorite language. Operator may use some command line tool to talk via over REST API. And some OpenStack, some cloud software uses its own program. And there can be your own SDN applications. So Ryu uses AIOs and threading heavily for simplicity. Ryu uses eventlet for threading and AIO, asynchronous I/O. Basically, this choice is done because OpenStack does it. In fact, OpenStack firstly uses twisted, but it switched from twisted to eventlet because twisted is too complex. So resulted code was too complex. So we studied we studied OpenStack. So we use eventlet from eventlet. We didn't adapt twisted. At first, we chose to use the event for performance, but we switched to eventlet for PyCon. So I'd like to talk about its Ryu. I think Ryu. Event dispatcher is represented by app manager and Ryu app class. It is the guts of Ryu. It is the essential core. So it decouples event source and sources and sinks. Event source generates events, and the event is passed to event source generates events, and the event passed to event dispatcher, and the event dispatcher determines which handler to deliver based on class of events, and it dispatches to event sinks. So event source is just event source can be any component of Ryu. So in order to generate events, just call method of the event dispatcher. And the event sinks, on the other hand, event sinks class of event syncs is abstracted as class up, and the event dispatcher knows which methods are interested in which events by introspecting its method attribute. And the event handlers are invoked in its own context of its own thread context of each app. Our event is dispatched to event handler. At first, our event is queued to its queue, and the dedicated thread, event thread, event thread consumes its event. This thread is introduced to avoid race condition, but this thread imposes some restriction of restrictions on event handlers. So event dispatcher provides some request reply style communications. Event dispatcher provides helper functions for request reply style communications. It is sometimes we'd like to implement some features with several Ryu apps. So we'd like to make several Ryu apps to communicate. Sometimes it is very hard to use event system with free event system with free asynchronous nature. So some synchronous communication is provided. When a Ryu app wants to communicate with other Ryu app, it can queue request event to other Ryu apps, and then it blocks for reply. It will wait for reply, and then request application and process the request and send back to the reply, and then blocked thread will be waked up, and then it will continue to execution. Okay. Next, I'd like to talk about OpenFlow parser and its event. Ryu implements only controller part. It doesn't provide a switch part because it doesn't not need it. And OpenFlow event is created automatically on Ryu startup. At this point, introspection is used. So there is no event for OpenFlow packets explicitly. It is very frequently asked, where is OpenFlow event is defined? No, there is no. The answer is there is no such place. It will be, they are created on startup. So next big part is OpenFlow switch management. It is managed by class OpenFlow controller and data bus. And it creates 2 threads to handle OpenFlow connection. And one is for sending packets, and one is for receiving OpenFlow packets. When packet is received, it is passed and converted into OpenFlow events, internal OpenFlow events, and dispatched to Ryu application. So next, I'd like to talk about OpenStack support, OpenStack integration. Probably not. There are several people those who are not familiar with OpenStack. OpenStack is a cloud software. You can build your own cloud with OpenStack. OpenStack is composed of many projects, and and the component service, compute service is covered by Nova project, and storage is covered by Swift or Glance or Cinder, and identity is covered by Keystone. Network service is covered by Neutron. Now, Ryu project is interested in network project, Neutron project. Former Neutron is named by Quantum, but because of trademark issue, it is renamed to Neutron. And Neutron is designed based on plugin architecture, so it is able to support many different network technology, like hardware switches or Open vSwitch, and Neutron supports many OpenFlow controllers and other many technologies. And Neutron has a Ryu plugin, and it is already merged into the upstream. So Neutron can be used with Ryu out of the box. Ryu plugin provides L2 isolation and multi-tenancy with or without VLAN. So you don't need any high-end switches. This L2 isolation and multi-tenancy can be used with a common chip switch. This this slide shows how Ryu plugin is organized. I'd like to say Ryu plugin works with Open vSwitch, and under Open vSwitch, and underlying hardware network can be commodity one. And Ryu and other components talks over many protocols, REST API or OpenFlow or OVSDB protocol. The core is when a network is created, that is, you create your own VM instance. It is created in Neutron server, and it is told to Ryu server. And it will configure OVS switches accordingly. Okay, I'd like to explain what is L2 isolation. In cloud software, there are many users, and users doesn't know each other, so they must be isolated from each other. So network should be isolated in some sense. So in this case, packet by L2 isolation. Packet can't be reached from one tenant to another tenant. So network, from user's view, user can think of network is can be occupied. But in reality, in physical view, it is very complex. In cloud, hardware, a server is shared, and the network is shared, and between network devices shared. So we need to differentiate the which tenant the packet was originated. We use when GRE tunneling is used, GRE tunnel key is used to identify the packet. And based on when sending a packet from a VM, GR key is assigned, and then the packet is forwarded to the network. And when a packet is received, the packet is identified by based on jar key and determined to which VM to deliver. So network is isolated at its level. This picture shows how OpenFlow release is installed. This is very details. This is the details of its implementation. So I won't explain in this. So in fact, I'd like to show the organization of its OpenStack integration. It is composed of 4 real applications, and they are very loosely coupled by using event system. Okay, I'd like to introduce Ryu development process. Its Ryu project is open project, and so anyone can involve its development. Its development model is based on Linux style because many core developers are Linux developers, so Linux style is adapted. So discussion or patch reviews are done on mailing list. So please use Git format patch or Git send patch. Please do not use pull request on GitHub. Okay, as last, I'd like to share my experience, Python experience. In fact, basically, I think Python is a good language, very easy to use and very useful. I found many features of Python is very useful, and I found some few bad things. It is hard to debug, and some magic attribute is ugly, I think. Okay, I'd like to explain about AIO threading libraries. At first, we used G-event, but switched to eventlet. G-event or eventlet uses monkey patching. In general, monkey patching is a bad idea, and it is very fragile. But surprisingly, eventlet or G-event works very well. But we hit some issues, and some patches are sent to upstream G-event or PyPy. Threading. In fact, I found threading of G-event is somewhat difficult to handle. Effectively, threading is cooperative threading due to giant interrupt lock. So it is difficult to manage. And I found it is hard to debug. When debugger is activated, eventlet try to switch to another setting. So it is effectively unuseful to use debugger. Probably it is due to my lack of Python skill. We evaluated real performance. So the result is its performance is not good compared to another OpenFlow controller, which uses pre-compiled program, and which uses full threading for performance. This is expected result, so this is not surprising. But we want as much performance as possible, so we try to use another radical performance. We tried another approach for performance boost. So we tried to PyPy. So we need to switch to use eventlet. But recently, CPU comes with many cores, so we'd like to utilize multi-core features. So some other another approach would be needed, but it's under investigation. So I'll skip this slide. Okay, that's it. Any questions or comments? We have 10 minutes or so. Yes. Yes. Sorry, louder, please.
My question is on applications not mentioned in your talk.
Yes.
I'm interested in SDN because the whole network status is maintained by the controller, and so SDN allows us to verify the network. I mean, we can check the correctness of the whole network status by SDN. This is an amazing thing for network people. And if I remember correctly, NTT Communications showed a demo of network verifications using Ryu in Interop Tokyo.
Yes.
My question is, are there any applications for Ryu related to the network verification? Do you know someone?
At this moment, released Ryu doesn't have such application. You can, of course, you can build your own such application.
I know.
Yeah.
Okay.
So I'd like to mention this presentation represents my personal view or opinion. This presentation doesn't represent Ryu project or any companies.
Thank you.
Any others? Okay, thank you very much.
Thank you for listening.
So I'd like to close this session. We will have lunch break till 30 o'clock. The afternoon session will be start at 13. And if you are a student participant and want to be a refund, please go to the secretariat room located in 4th floor. That's it. Thank you very much.